In this video abstract, we discuss our paper, The Relationship Between Road Traffic Collision Dynamics and Traumatic Brain Injury Pathology, which is research done as part of a collaboration between Imperial College London and the Transport Research Laboratory. We were able to relate data that car sensors can record to the risk of different traumatic brain injury severities and pathologies. This is a foundation to relay brain injury risk to the emergency services in real time. Road traffic collisions commonly lead to traumatic brain injury, which is a leading cause of serious injury and death. Brain injury is particularly time-dependent. After the initial injury occurs, brain injury severity can worsen with time. Direct transfer to a site with neurosurgical provision has been shown to reduce mortality from 36% to 19%. Knowing which road traffic collision casualties are at high risk of traumatic brain injury could guide the pre-hospital emergency service response, improving outcomes, saving lives. In Europe, most new vehicles are fitted with sensors that automatically notify emergency services to the location of a collision. This enables the emergency services to arrive at the site of the collision faster. However, nothing is known about the possible injuries. In this paper, we show a relationship between the parameters from collision data that can be recorded by car sensors and traumatic brain injury severity and pathology. We use extremely detailed in-depth historic collision data, which includes clinical, vehicle, and environmental information. There are over 5,000 subjects contained in the database. We then apply a novel free text search to identify all brain injuries, for example, looking for terms such as basilar skull fracture or subarachnoid bleed. We use these data input parameters to determine traumatic brain injury risk. We constructed logistic regression models that predict traumatic brain injury risk from collision data. We determined risk for car occupants and a pedestrian cyclist group. Change in velocity, delta V, is recorded by car sensors and modelled injury risk well. For car occupants, the direction of change in velocity affects brain injury risk. Subjects in collisions with higher lateral change in velocity, delta V, are at greater risk of mild to moderate severe brain injury. Including a direction indicator in the model improved the prediction accuracy, in some cases as high as a ROC AUC 0.95. We focused on high-risk groups such as pedestrians and cyclists. The detailed clinical and collision data also enabled us to analyse helmet use and effectiveness. Cycle helmets protected against mild to moderate brain injury overall, skull fracture, and subdural hematoma. This protective effect was not due to differences in impact or travel speeds between helmeted and unhelmeted groups. In conclusion, our work demonstrates that collision data parameters that car sensors are capable of recording can be used to predict traumatic brain injury risk. Vulnerable road users are at higher risk of brain injury, but helmets are protective. Finally, we would like to thank our funders, collaborators, and data providers who make this research possible.